There's something really fascinating about synthetic division, and it's not readily apparent when you first look. It'll be apparent if you watch closely a method of evaluation for functions called Horner's rule. So if you want to pause the video and look at that, you can, but I'm going to zoom in on this little function here, and I'll just show Horner's rule to you. I notice that there's a common factor x in all but the last term. So I'm going to factor out the common factor x, and as I do, I would leave myself with a 3x to the third power minus an x squared minus a 3x minus a 5, and then I'd still have to have the minus 7. Now, I'm going to copy the x, and I'm going to copy the minus 7 and the minus 5 that's right here. And then I notice that these terms here all have a common factor x, so I'm going to factor that common factor x out. That would leave me with a 3x squared and a minus x and a minus 3. And you can prove every factoring by simply distributing through, multiply, and see that it gives you the thing above. So I'm going to copy this x, and I'm going to copy this minus 3 here, this minus 5 here, and the minus 7. And I notice that these two terms here have a common factor x in them. So I'm going to factor out that common x, and that would give me simply a 3x minus 1. And it looks so strange when you see it. But I'm going to show you a simple evaluation. Let's suppose that we wanted to evaluate our function at 2. So what would f of 2 be? And simply we would replace all of these x's with 2's, and there'd be a whole lot of places to make those replacements. And I'm going to copy all the structure of our original problem now, and then we'll see if we can evaluate it. So I'll write in order what we're going to do. We're going to take this 2 times 3 and get a 6, subtract 1. Then we're going to take that times this 2 right here, and that'll give us a 10. So now it's time to evaluate. But before I do, I'm going to set up a synthetic division table. And the synthetic division table will just take the coefficients 3, minus 1, minus 3, minus 5, minus 7, and I am going to do a synthetic division with that same 2 that I was using for my function evaluation. So the synthetic division table brings down the 3. That's our first step. And from this point out, it's going to be a multiply followed by an add. So in the synthetic division, I'm going to do 2 times 3 is 6, and then 6 minus 1 in the column is a 5. Now look over here. 3 times 2 is 6. 6 minus 1 is 5. Now what am I going to do with that 5? Well, I'm going to do 2 times 5 is 10. Add that column is a 7. Now come back over to Horner's rule. What am I going to do with this 5? Well, I'm going to multiply it times that 2. That would give me a 10. And then that would be a 10 minus the 3 that was still inside this level of parenthesis, and that would give me a 7. So this has all become a 7, just like in the synthetic division table. In the synthetic division, I'd now do 2 times 7 is 14. Add the column, negative 5 plus 14 is 9. Now let's go back to Horner's rule. What am I going to do with this 7? Well, I'm going to multiply it times that 2, and that would give me a 14. And then I'm going to subtract that 5 from the answer, and that would give me 14 minus 5 is 9. Did I say that was 7? No, I said it was 9. So it was just like it was in the synthetic division table. So one last step, 2 times 9 is 18, and then negative 7 plus 18 is an 11. Now let's go back and look at Horner's rule. What am I going to do with this 9? I'm going to multiply it by that 2 and get 18, and then 18 minus 7 is going to be the 11. So the remainder, when I do synthetic division is my function evaluated at the synthetic divisor. So f of 2 would equal 11. So would you rather take a 2 and plug it into the original expression here and evaluate that expression, or would you rather do a synthetic division? So we'd rather do a synthetic division. Now before we go any further, let's try it. So we'll prove this one of two ways. I won't use Horner's rule on this one this time. Horner's rule is used just to justify that synthetic division is the same thing as function evaluation. So let's find f of 2 by synthetic division. So we would take the coefficient pattern and set up a synthetic division table, and would use the actual number, the 2. That's the hard part about this, is that in division we always use the opposite number of the divisor, but this is not a division. This is just a function evaluation. Use the number that you're asked to find. So down comes the 3. 2 times 3 is 6, add the column 1. 2 times 2 is 2 times 1 is 2, add the column 4. 2 times 4 is 8, add the column 1. So f of 2 is 1. Now let's try it over here. 3 times 2 to the third power minus 5 times 2 to the second power plus 2 times 2 minus 7. Let's see. 2 to the third power is 8. 8 times 3 is 24. 2 squared is 4. 4 times 5 is 20. 2 times 2 is 4. And then take away a 7. 24 take away 20. That's 4. 4 plus 4 is 8. 8 minus 7 is 1. Yeah, either way I'm going to get a 1. So synthetic division is the same thing as evaluating your function. So let's try one more. Set up your synthetic division problem. And the only trick you have to remember is that we don't change the sign when we're doing a function evaluation. We just use the number that we're asked to evaluate. So negative 3 times 1, negative 3. Add the column negative 5. Multiply positive 15. Add 16. Negative 3 times 16 is negative 48. Add the column negative 51. Negative 51 times 3 is positive 153. Add the column 157. And even though those numbers are kind of large, you could do a calculation with your calculator, and that would be much, much easier than trying to substitute the negative 3 into that formula. Now, there's some tricks that we need to be aware of. And the tricks are kind of obvious, and it is how to evaluate your function at 0, 1, and negative 1. So pause and read. Whenever I evaluate at 0, notice that all calculations with 0 result in 0. So 0 to the third times a multiplier of any sort, all of this stuff would go to 0, and all you're left with is the constant. So that's the trick for f of 0. It's just the constant at the end. Now f of 1 is a similar trick, but you have to know something about multiplying with 1. Multiplying with 1 never changes values. All powers of 1 are 1. So f of 1 is when I simply take the coefficient pattern, negative 2, 7, 2, and negative 5. And I just add the coefficient pattern, because 1 to the third power is 1. 1 times negative 2 is negative 2. There's the simple justification. So when you're trying to evaluate your function at 1, just pull the coefficient pattern out of it and add it up. Look for a couple of shortcuts there. Notice that the negative 2 and the plus 2 would go to 0. 7 minus 5 is 2. So f of 1 is equal to 2. Now f of negative 1 is based on this concept. Negative 1 to the first power is negative 1. Negative 1 to the second power is equal to positive 1. Negative 1 to the third power is equal to negative 1 again. Negative 1 to the fourth power is equal to positive 1 again. So, simply put, and it might make it a little easier if I would copy the function rule over here, just so it's in the same same region on the screen. And for every odd power, and be sure that you understand that the linear term 2x is considered an odd power. For every odd power, the negative 1 to an odd power would equal negative 1. And when you multiply by negative 1, it switches the signs. So to evaluate your function at negative 1 quickly, you simply take all the odd powers and you switch the sign of the coefficient. So 2 plus 7 minus 2 minus 5. And notice again that I've got a couple of things that would go to 0, the 2 minus 2, and then 7 take away 5 would be a 2, so f of negative 1 would be a 2. So it's just a quick way to evaluate our function. Now, here's how we put it to work. Whenever we're trying to analyze an equation or a graph, a function, then the number of sign changes is the maximum number of positive roots that the equation can have. And then if I switch the odd power signs and count the sign changes again, that'll tell us how many, the maximum number of possible negative roots that your equation can have. So here's the way that we put it into practice. You count the sign changes, change the odd powers, count them again, and it gives you an insight into how many solutions you're likely to find. And notice that it says more on that later, so let's don't get too involved with that now. But here is the question that we answer all the time. How do you solve not just quadratic equations, but anything above the first power? You always set them equal to 0, factor them, and set the factors equal to 0 and solve. So that's what we're going to do. So before we go too much further, notice that it says for these problems, all the problems on this assignment either have a solution of x equal 1 or x equal negative 1. So my first question is, if I think of this as a function, x cubed minus 2x squared minus 5x plus 6, what is f of 0? 6. What is f of 1? Well, just add 1 minus 2 minus 5 plus 6. So f of 1 is equal to, well, that's 7 minus 7. That's equal to 0. That's a 0 of the function, meaning that x equals 1 is a solution. Now, if x is equal to 1 is a solution, it means that x minus 1 is equal to 0, and x minus 1 is a factor. Now, this is still new, and you're going to struggle a little bit as you grapple with this concept of the function evaluation versus the function factor. So this is where the question comes in, what is a solution? And a solution simply is something that makes a true statement. This little routine right here demonstrates that x is equal to 1 is a solution. And if we have a solution at x equal 1, that's the equivalent of having a factor of the x minus 1. So in the synthetic division table, I'll see two things happen here as I do the table. My synthetic divisor is going to be the 1 that corresponds to the solution and also corresponds to the remainder. So the synthetic division process is quick to go through. 1 times 1 is 1, leaves a negative 1 in this column, a negative 1 again, then add the column is a negative 6, multiplies a negative 6, and the remainder is a 0. So that 0 is two things. It's the proof that x equals 1 is a solution. Remember, a solution makes a true statement, and if I put 1 into that expression, out comes a 0 for the final evaluation. But it also indicates that I have an x minus 1 factor, and the other factor being x squared minus x minus 6. And remember, this is in the context of an equation. So I'm going to fully factor my equation. The second part of this factoring should not be particularly challenging. In this case, it's an x minus 3 and an x plus 2. So here are my three solutions. X equals 1, x equals 3, x equals negative 2. And I was able to find those with relative ease, even though that looked like a pretty complicated equation. So let's try another one. For this next equation, it has to be set equal to 0. Let's move some terms. X to the 4th power plus 3x to the 3rd power minus 17x squared minus 39x minus 20. I moved them to the left side by subtraction, equals 0. So let's just find f of 1. So we take all of the coefficients and simply add them together. 1 plus 3 minus 17 minus 39 minus 20. Now, you can see that there's a positive 4 in the 1 plus 3, and all of these other negative terms would be a quite large negative number. And all I need to be aware of is that that would not equal 0. So let's find f of negative 1. So this time, if it has an odd power, and remember the x is an odd power, it's x to the 1st power. If it has an odd power, switch the sign for the evaluation at negative 1. So coefficient of x to the 4th is 1. Switch the sign of the x to the 3rd coefficient. Keep the sign of the x squared the same. Switch the sign of the 1st power x from negative 39 to plus 39, and then the constant at the end remains. And when I'm doing evaluations like that, I always like to get my positive numbers and get them into a single answer. So 1 plus 39 is 40. And then I see here that I have a negative 3 and a negative 17. That's a negative 20. And then another negative 20 over there. So I would have 40 minus 40 equals 0. F of negative 1 is negative 0. Now, that should tell you immediately that x equals 1 is a solution, because if I exchange x with a negative 1, it'll work out to equal 0. In my factoring, that indicates that I have an x plus 1 actual factor, but a solution at negative 1. So while this remains new, you're going to have to struggle to know when do you change that sign and when do you keep that sign the same. So on my synthetic division, when I do the synthetic divisor of negative 1, I'm finding the function value at negative 1. I'm evaluating this expression for negative 1. So I expect to see a big 0 down here that indicates that negative 1 in the formula gives the answer 0, therefore is a solution. But let's just prove it. Negative 1 times 1 is negative 1, add the column 2, multiply negative 2, add the column negative 19, multiply positive 19, add the column negative 20, multiply positive 20, add the column 0. So that means that I do have an x plus 1 factor, and the other part will be x to the 3rd plus 2x squared minus 19x minus 20. And that would still equal 0. Now we have to factor that other part because it has our other solutions. And how in the world can we do it? So the first obvious thing that I would suggest to you is that it doesn't fall into any of the common factoring patterns. So let's try one of these more recent tricks. If I focus only on this part of the problem, the x cubed plus the 2x squared minus the 19x minus the 20, and I evaluate this as a function, what is f of 1? The coefficient pattern will be 1 plus 2 minus 19 minus 20, and I can tell that would not equal 0. So let's try to evaluate it at negative 1. So if I evaluate it at negative 1, all the odd powers would change the coefficient, become negative 1 plus 2 plus 19 minus 20. And I see that this would give me a positive 21 and a negative 21 and equals 0. So there is a second factor and a second solution at negative 1. So let's set up a synthetic division table again for the cubic polynomial 1, 2, minus 19, minus 20. And again, we're going to do a synthetic divisor of a negative 1. And again, we expect to see a 0 over here because we've already done the work. Let's just see what the rest of it makes. Multiply negative 1, add the column 1. Multiply negative 1, add the column negative 20. Multiply positive 20, add the column 0. So here's what we have then. We have the x plus 1 that we've already factored. We just bring it down. We have another x plus 1 corresponding to the factor indicated by the synthetic divisor negative 1. And we have x squared plus x minus 20. And still in the context of an equation, still equal to a 0. So if we would do one last little thing, we'll be all done. And the last little thing, we're down to a second power polynomial, and that typically indicates that we'll have FOIL factoring. 4 times 5 is 20, so a plus 5 and a minus 4 would give us the plus 1x that we see. So now we're ready to state all our solutions. We have two solutions at negative 1, and we'll talk much more about that double root or that double solution at a particular point later. And then we'll also have a solution at x equal negative 5 and x equal positive 4. So those are all our solutions, and that looks like a pretty daunting problem. There are some things that we can do that can make it easier, and that's what these little tricks are about. So remember, it's always going to be set equal to 0 factor and set each factor equal to 0, but what can give you some insight is to remember these little tricks here, that if I want to evaluate my function at 0, at 1, or negative 1, there are some shortcuts that can get that.